Whenever I was learning something in maths, I always wondered why on earth someone would want to come up with this stuff. For a lot of us, maths is just something to get through. An exam, an assignment. But for the people who came up with these techniques, they were solutions to real problems. So today we're going to find out why Gauss bothered coming up with the method of ordinary least squares. This is Ceres. On the first night of 1801, an astronomer in Palermo called Giuseppe Piazzi noticed a faint point of light that wasn't in any star catalogue at the time. The next night it had moved. He had tracked it for 41 nights, writing down where it was each time. Then it drifted too close to the sun and he lost it. To find it again, someone had to work out its orbit. And an orbit is only a handful of numbers. How big it is, how stretched it is, and which way it is tilted. He had 41 observations for a handful of numbers, which was more than enough. Except every one of those 41 observations is slightly off. Not by much, but enough that no orbit passes through all of them. Whichever orbit you try, it misses most of them. But an orbit has to be chosen, even though none of them fit exactly. This is the problem that Gauss was trying to solve. The question is, on what grounds do you choose an orbit? Gauss's version of this problem is an orbit through observations. We're going to do the simplest version, which is a straight line through points. Whatever we work out for the line carries over to the orbit. Say we've got 5 measurements. Each one is 2 numbers, for example height and weight, so each one is a point on a graph. We want the straight line that runs closest to all 5. No line goes through all of them. Whichever line we draw, most of the points sit above it or below it. The gap between a point and the line is how far the line misses that point. So before we can choose a line, we need a number that says how badly a line misses. For one point, the gap between it and the line is positive when the point sits above the line and negative when it sits below. That gap is called the residual. Adding the residuals up won't do. A line can still miss every single point and still score near 0 because the misses above cancel the misses below. So we ignore the sign. We take the size of each gap and add those. That does work and plenty of people use it. The whole point of this total though is to find the line that makes it as small as possible. And the way to find the bottom of something is to differentiate it and set that derivative to 0. That only works if the total has a gradient at its bottom, and a total made from sizes doesn't. The easiest way to see why is to forget the line for a minute. Say 3 friends live on the same street at number 1, number 2 and number 5, and we want to stand where the total walking distance to all 3 is the smallest. Walking towards the house at number 2, the distance to it shrinks by 1 for every step. Walk past it and the same steps make the distance grow by 1. So the distance graph to any house is a V shape with its corner at the house. A distance can't be negative, and that's where the corner comes from. The total distance is 3 of those V's added together with 1 corner at each house. Between the houses, the total moves at a fixed rate. Starting before number 1 and walking along, the distance falls by 3 each step, then by 1 a step, then after number 2 it rises by 1 a step, then by 3. So it can't bottom out between houses, because between houses it is still falling at the same rate step after step. It can only stop falling where the rate changes, and the rate only changes at a house. The bottom is at number 2, and at number 2 the rate jumps. 1 step before the total was falling by 1. 1 step after it's rising by 1. There's no step where it's flat. So there's no gradient to set to 0 and no equation to solve. Now the squared distances. A squared distance has no corner because the square of a small distance is tiny, so the curve flattens out as it reaches the house instead of hitting it at an angle. Add 3 of those and the total is a curve with 1 bottom, and at that bottom the gradient passes through 0 instead of jumping over it. Set it to 0 and we get an equation. Turning back to the line, each point has a slope at which the line passes straight through it, and the size of its gap is a V with its corner at that slope, exactly like the distance to a house. So the total of the sizes have 5 corners, the bottom sits at 1 of them, and the gradient jumps there. Squaring the gap swaps the 5 V's for 5 curves, and the total's gradient slides through 0 at 1 slope. That's the one we solve for. There's a picture for this. Each gap is the side of a square. The total we're adding is the total area of those squares, and the line we want is the one that makes that area as small as it can be. That's where the name least squares comes from. The total area depends on which line we drew, and the line is 2 numbers. The slope and the intercept, which is where it crosses the y-axis. So we're going to need to find the minimum of the sum of the squared residuals with respect to the slope and the intercept, and to do that we're going to have to take partial derivatives. So far the slope has been the only thing moving and the intercept was fixed at 1. That parabola lives on two axes. Slope along the bottom and the sum of squared residuals up the side. Change the intercept, say to 2, and every gap changes, so the sum changes and we get a different parabola on the same two axes. Change it again and we'd get another one. They'd all pile up on top of each other, so we give the intercept an axis of its own, coming out towards us, and slide each parabola out to its own intercept value. Now there are three axes. Slope one way along the floor, intercept another way, and the sum of the squared residuals as the height. Sweep the intercept through every value and the parabolas sit side by side along that new axis, close enough to fill in a surface. That surface is the sum of the squared residuals for every line we could possibly draw. Pick any slope and any intercept, and the height of the surface above that spot is the sum of squared residuals for that line. Two things pin down its shape. Every term in the sum is a square, so the surface can never dip below 0. And if the sum or the intercept runs off to a silly value, the line runs away from the points and the sum shoots up. So the surface comes down from every direction to one lowest point. It's a bowl, and the slope and the intercept sitting underneath that lowest point is the line that we want. At the bottom of a bowl, the ground is flat. Not just flat in one direction. Walk off any way you like and you go up, so every direction is flat right there. That includes the two directions along the floor, the slope direction and the intercept direction. So we take those one at a time. Hold the intercept still and let only the slope change. That's a slice through the bowl, and the slice is an ordinary curve with an ordinary gradient. At the bottom, that gradient is 0. Then hold the slope still and let only the intercept change. That's the other slice, and its gradient at the bottom is 0 as well. Differentiating the sum with respect to one of those numbers whilst holding the other still is what a partial derivative is. It gets written with a curly d instead of a straight one, and the curly d means exactly that. The other number is being held still. So we have two partial derivatives with both being 0 at the bottom. That gives us two equations and we have two unknowns. We'll take the intercept first. The partial derivative with respect to the intercept measures how fast the sum of squared residuals changes when the intercept goes up a little and the slope stays the same. Raising the intercept with the slope fixed moves the whole line up, parallel to where it was. So every gap changes by the same amount. The gaps above the line get smaller and the gaps below it get bigger. Working that through for the squares, the derivative comes out as minus 2 times the sum of the residuals. At the bottom of the bowl, that derivative is 0, so on the best line the residuals add up to 0. The misses above the line exactly balance the misses below it. If the residuals add up to 0, then the actual y's add up to the same total as the line's predictions, so they have the same average. And the average of a straight line's predictions is just its predictions at the average x. So the line's prediction at the average x is the average y. Whatever the slope turns out to be, the best line passes through the average point. The partial derivative with respect to the slope measures how fast the sum changes when the slope goes up a little and the intercept stays the same. Raising the slope with the intercept fixed pivots the line about the point where it crosses the y-axis, so the line rises more at points further from that axis. Each gap changes in proportion to its own x. Working that through, the derivative comes out as minus 2 times the sum of x times the residual, and at the bottom that's 0 too. So on the best line, the residuals weighted by their x's add up to 0. Those two conditions pin down the two numbers. The first one says that the line passes through the average point, so we can measure everything from there. Shift the origin to the average point. Now the line goes through the origin, so its intercept is 0, and the only thing left behind to find is the slope. Written in the new coordinates, the second condition turns into a formula for it. The slope is the sum of u times v, divided by the sum of u squared, where u is each point's distance from the average x, and v is its distance from the average y. The bottom of that formula is how spread out the points are across. The top is how much the two quantities move together. A point that's above average on both, or below average on both, gives a positive. A point that's above on one and below on the other gives a negative. So the slope is how much the points move together, divided by how spread out they are. Those are the two numbers. So we run it on our 5 points. So here are our 5 points with their averages. The average x is 3 and the average y is 7, so the line goes through 3, 7. Measured from there, the products on the top of the slope formula add up to 20, and the squares on the bottom add up to 10. So the slope is 2. And the line with slope 2 that passes through 3, 7 crosses the y-axis at 1. So the line is y equals 2x plus 1. That's the whole method. Gauss did the same thing with an orbit instead of a straight line, and Piazzi's observations instead of 5 points. An orbit has more numbers to find, so there are more partial derivatives to take, but the idea is the same. Gauss picked the orbit that made the squared misses as small as they could be, and then he worked out where that orbit would put the planet by the end of the year. He published his predicted position. On the last night of 1801, astronomers pointed their telescopes to where he'd said, and there it was. That's Ceres. It had been lost for nearly a year, and it was found again with a calculation. So that's why Gauss bothered. Observations never agree with each other exactly, and a line of best fit still has to be chosen. Least squares is a way of choosing that you can actually solve. But there's a choice in here that we never justified. We squared the misses because it got rid of the sign and because it left us with something that we could differentiate. Both of those are about making the algebra work. Neither of them is about the measurements. And squaring does something. A single miss of 4 costs 16. 4 misses of 1 costs 4 between them. So we've decided that one bad miss matters more than several small ones. There is a reason for this, and it's to do with how the errors are spread out. That's the next video.